Okay, I think I can get started. And really
Yeah, great.
appreciate the opportunity from the editors
Yes,
and the committee. Uh, I'm really glad to have this chance to share with others about our recent work on soft smart materials with multi-scale architecture and dynamic surface topographies. I will start with a very brief introduction of the story that I would like to share with you. I will share with you three stories, basically, well, maybe four. I have one, two, three, four, but the first one is basically some fundamentals, and the last one goes back. So, uh, we are working on coating research, and during our coating research, we found some pretty interesting phenomenon. Basically, if we can control the surface topographies and also particularly the architecture, we can generate some very interesting optical properties, which is probably not new to many of uh, the researchers in the audience. But ours is a little bit special. So first of all, for the coating, what we generate is the coating with naked structure, and we can of course, keep the coating intact, but we can also generate micro cracks if we stretch it, or if we just gently stretch it or gently swell it to generate micro wrinkles. And on the other end, if we have the coating on a very rigid substrate, it can change the thickness. So I basically will share with you three stories about these different surface topographies and morphologies. So I will first briefly tell you how we make this coating. The coating was made through a so-called one-step co-assembly process, which is a very simple, very efficient process to align nanosheets on the surface. And here are some TM images of the cross-sectional areas. As you can tell, we can generate a very high concentration, but also meanwhile highly oriented nanostructure, which is very important because with nice orientation, with the control of the concentration, and also we have C, which means cross-linking. With this three control, we can generate coatings with very broad mechanical properties, from very ductile to very rigid, and could be very soft or be very fragile. And therefore, with this, we can easily to crack them to make so-called micro cracks. And those micro cracks can be took advantage to make so-called mechanochromism or thermal management. So here is basically the general idea. We can alter the stiffness and the toughness so that we can easily crack them or generate wrinkles to achieve the desired morphology for different applications. But before I talk about mechanochromism, I will give you a brief introduction about the background. Mechanochromism is a very interesting field of research. Basically, that means when you apply a force to a material, the material will generate a color. For example, this is a material called spiral pyron. When you apply force, it will generate a beautiful light blue color. So this is absolutely a very interesting field of research. These materials are very unique, but on the other end, they have some weaknesses. Number one, they are very difficult to synthesize. Number two, it requires very high strength to generate color. And number three, because of the very high strength, the deformation is way beyond the elastic deformation, so the color change is not reversible. But the biggest challenge in the field is the difficulty to tune the color. For example, this is the material called spiral pyron. It can generate a light blue color, which is great. But if you want a material to generate a yellow color, pink color, then you need to redesign the material, which is very difficult. So this is basically a big headache in the field. And actually, my group never initially target to solve this problem, but about 5-6 years ago, during one of the ACS meetings, I believe, we witnessed this beautiful video. I trust many of you in the audience watched this video before. This is a sea plant at the bottom of ocean. This part not moving around, which is the octopus. And some of you may or may not be aware of that. Octopus has a very amazing capability to change its skin color and texture and shape. Well, you may understand that it's easy to change its skin shape, but actually octopus can also change its skin color. The reason is actually very simple, and it's kind of hard to imagine. But basically, in the skin, there are a lot of pigments which are encapsulated by muscle of octopus. And whenever the octopus contract their muscle, you can see virtually no pigments. Those tiny dots are completely blocked. But when it relax their muscle, you can see those big dots. So basically, the display phenomenon or the mechanism is very simple. Basically, it's all based on the physical blocking. And so when we do coating research from time to time, we notice that we will generate micro cracks. And based on that, one of my previous co-workers, now a professor at Macau University of Science and Technology, Songshan, figured out a very innovative idea. He figured that maybe we can just hide the pigments behind the coating and use the pigments serving as a function like window blinds. So whenever you stretch to open the window blinds, you can see the color behind it. When you release to close the window blinds, then you cannot observe the color behind it. And therefore, to generate such a very simple physical blocking mechanism. So this is basically how we made the material based on the explanation I showed you just now. So we would like to have a soft substrate so that we can stretch it, and we use PDMS, which is a very versatile material. On the very top, we put a coating. I showed you the coating which we can alter the stiffness and the toughness so that we can easily stretch to crack them to form micro cracks. And of course, in between the coating layer and the substrate, we have a very strong interface through the crosslink. And in this way, we will only generate cracks, but no delamination. So here, at 40% of uniaxial strain, you can observe the formation of the micro cracks, like here. But when you release the sample, go back to 0% of strain, all the cracks will be closed. So they will not be healed, they will just be closed. And with this very simple phenomenon, we can make something pretty interesting. So first of all, we can change the transparency of the material. Because whenever we stretch it, the many numerous micro cracks can scatter and diffuse light, and therefore it will generate an opaque appearance. Like here, you can imagine with all those micro cracks, they can generate light scattering and diffusion. But on the other end, those micro cracks can trap air, and with air in those micro cracks, it can generate so-called lotus leaf effect, and therefore the surface tend to be very highly hydrophobic, which is also very ideal for many applications. So here, let me show you the real mechanochromium. So as I told you, our idea is very simple. We try to block the pigment using a thin layer of coating. And now, in order to more effectively block the pigment, we add some titanium dioxide, which is a very good light blocking agent. And here, as you can tell, before we stretch it, this is the intact coating layer without micro cracks, and therefore it blocks everything behind it. But when we gently stretch it, we open the micro cracks. It's kind of like open the window blinds so that you can observe the color behind it. And this is a very simple device, as you can tell. Very, very simple, but on the other end, it's highly sensitive. It only requires 3-4% of strain to generate the color. But the biggest advantage for this design is that now we can generate color at will, whatever color you want, yellow, green, orange, blue. You can only just mix the pigments into PDMS matrix, and then you can generate any color, and that is very versatile for real applications. Another advantage for our design is that we can change the color. For traditional mechanochromic materials, it can only generate color. Basically, it's the same color from color A to color B with different, the same color from intensity 0 to intensity, very high intensity. Basically, that's the intensity change. But with our design, we can actually change the color from color A to color B. So here, what we did is that on the very top of the coating, we deposit a second pigment layer. So for example, here, we have a layer of green. So before we stretch it, you can only observe the green color. The underneath orange color is blocked by the titanium dioxide coating layer. But during the stretching process, as you can imagine, with the opening of the micro cracks, the intensity of the green color going down, and the intensity of the orange color going up because more and more exposure. So this is like you are mixing two pigments with different ratio on your plate, and the combination is color change if you do it continuously. So initially green and then to yellow and to orange. And on color coordinates, we can find that the color change is linear. So if the material is very uniform, we can generate a linear color change, and moreover, you can generate a different color change if you use, for example, a blue color and a red color as a pair. It will change from blue to white to pink to red. And therefore, it offers different opportunity to generate color change for other applications. And of course, if we generate a color change regionally, then you can generate patterns. For example, here, this is a Yukon pattern. So with this very simple design, we can control basically the emission of the radiation. This is the electromagnetic radiation. And of course, we can control the radiation of many different systems, not just the electromagnetic, but we can also modulate the thermal radiation using the very similar design. So for example, if we do the thermal radiation, what we can generate is that through the opening of the cracks, we can generate temperature change, or I would say emissivity change, and then shown under the infrared microscope, infrared camera, you can see the change of the color, basically change of the temperature because of the control of the thermal radiation. So now I will move to the second story to show you that how we can also control to generate micro wrinkles. So if you stretch the material all the way, you can crack them to generate micro cracks, as I showed you just now. But if you stretch the material or you deform the material using either mechanical force or maybe other means like swelling, but do not break them, then if it go beyond the elastic deformation, the deformation will be too large to shrink completely back. And therefore, because of the mismatch of the top and the bottom layer, it will generate a wrinkled surface. And this wrinkled surface can generate similar interesting optical property changes. And I will show you some examples right next. So instead of using mechanical force, which has been well adopted, we mainly explored another means to generate wrinkle formation, basically is the swelling by moisture. The reason is because our coating layer is a hydrophilic coating layer made of polyvinyl alcohol, and therefore it is very sensitive to moisture. I trust that many of you have interesting experience that after a long shower or swim, you can find the observation, you can observe the formation of the wrinkles on your fingers. And this is simply because our skin has a similar bilayer structure. The top layer is thin, rigid epidermis, and the bottom layer is thick and soft tissue. And therefore, because of the deformation through the swelling, the top layer tries to deform and swell, but the bottom layer tries to prevent it. The compromise is the formation of the wrinkle surface. But we all know that the wrinkle formation on our finger is very slow. It takes like 15-20 minutes. But for the real application, we really cannot wait for 15-20 minutes. We want it to happen very quickly, hopefully within a minute or even quick. And of course, try to make this happen. One simple solution is to make the top layer very thin, because if it's very thin, the mass transfer will be very quick. So with that, we make a very thin top layer, less than 1 micron. And here you will find that with the spread of moisture, because of the swelling, it forms wrinkles, and the wrinkle generate light scattering and diffusion, so make the surface tend to be opaque. So it takes less than a second to form wrinkles and about 6-7 seconds for the wrinkles to disappear, to be erased because of the evaporation of the absorbed moisture. But of course, if you use some dry air or CO2 to spray the surface, then you can erase wrinkle real quickly too. So here you find that with the very quick formation of the wrinkles, it generates an opaque surface. It also generates some kind of interesting optical property changes. And plus, with the flow of the moisture regionally, we can generate wrinkles regionally, or we can erase wrinkles regionally. And therefore, again, we can generate patterns. So this is very, of course, ideal for many applications. But after talking to our industry collaborators, we were given an even more demanding requirement, because if you simply try to generate patterns like this, we can use other means. For more demanding applications, what we really want is to embed a pattern into a device in advance. And whenever it's needed, we can reveal it, we can show it. And whenever it's not needed, we should hide it and to protect it. So with that in mind, instead of just to generate wrinkles regionally, what we try to do is that we would like to embed a system which can form wrinkles whenever needed. So what we did is a very simple process called cross-linking, because without cross-linking, the surface is highly sensitive to moisture and very easy to form wrinkles. For example, the red zone, without cross-linking, it can form wrinkles very easily. But with cross-linking, it will be much more stable, and therefore you will not easily form wrinkles, but even just a little bit buckling. And so if we do regional cross-linking, then only the cross-linked zone, only the non-cross-linked zone will form wrinkles and therefore generate a pattern. So for cross-linking of PVA, fortunately, it's very simple. We can use chemical. We can also use UV radiation. And you can just cut a pattern or 3D print a pattern. And then we can use either UV or chemical to generate regional cross-linking, and therefore to allow for wrinkle formation regionally. The second consideration for this material design is the reversibility and kinetics. We all know that wrinkle formation on our finger is a reversible process, which is great. If not, I doubt many people will be bold enough to swing for a long time. But on the other end, we do actually occasionally, I would say actually, for majority of applications, we require reversible process, which is more ideal. But for some very special applications, we actually wish to have an irreversible wrinkle formation process. And I will show you some examples right next. And in fact, I would say, unfortunately, there is a very typical example of irreversible wrinkle formation in our life and nature, which is the skin formation, wrinkle formation on skin when we get old. So it is absolutely would be very interesting if we can have a deep understanding of wrinkle formation kinetics and reversibility, not just for this project, maybe also for this project later in the future. So based on all these considerations, we had 3 designs. The first one is reversible wrinkle formation. Basically, you can form wrinkles and you can erase wrinkles anytime. The second and the third scenario are irreversible wrinkle formation, but we have 2 different scenarios. One is to form wrinkles and then we can erase wrinkles completely. And the second is to form wrinkles and then wrinkle will stay there forever. It's kind of like a 2-way traffic. And this is one-way traffic. One go to the north, one go to the south. So this is the first example, which shows complete reversible wrinkle formation. We basically use a very thin coating layer, as I showed you at the beginning, which is a polyvinyl alcohol with clay. And the polyvinyl alcohol we use is the PVA from Curaria with a molecular weight of 87,000. And this is very versatile PVA, and therefore it can respond to moisture very effectively. Whenever we apply moisture to the surface, it forms wrinkles. Whenever we remove the moisture source, the absorbed moisture will be evaporated, and therefore the wrinkle will be gone. And in terms of transparency, you can find that with the wrinkle formation, it tends to be opaque, but with the erase of the wrinkles after the evaporation of the moisture, the surface will return to be very highly transparent. And of course, we can also generate a pattern through regional cross-link. So if we do regional cross-linking, only a certain region can form wrinkles, and this will generate a pattern when the wrinkle forms. And for example, here, if we breathe in front of the sample, let the sample absorb moisture, it forms wrinkles regionally, and it will form a pattern. So for the second scenario, we would like to generate wrinkles and then to erase wrinkles completely. And this is kind of more demanding, but we are lucky that the PVA we used polyvinyl alcohol happened to be highly sensitive to moisture, and it can be plasticized by water. Basically means with a molecule of water, PVA polyvinyl alcohol can gradually lose mechanical strength and tend to be very soft. And to make this even more effective and sensitive, we use the PVA polyvinyl alcohol with a very low molecular weight of 5,000. So with that, lose mechanical strength and be flattened by the substrate. And in terms of the transparency, that's the same. So when you apply moisture initially, it forms wrinkles because of the swelling. But gradually, if we apply excessive moisture, we can plasticize the PVA layer, make it very soft to lose mechanical strength, to be flattened by the substrate PD mass, to return to be transparent. And if we do a regional cross-linking here, then we can generate a similar phenomenon. So if we do the regional cross-linking, then the cross-linked zone cannot form wrinkles, but only the surrounding zone form wrinkles. You can observe the pattern of IMS. But if you continue to spray moisture, the surrounding wrinkle zone can be erased. And once the wrinkle zone erased, all will be gone, and therefore there will be no contrast. And so we can erase this pattern completely. One of my undergraduate students involved with this project too, Tom Doria, call it erase after read. And it's kind of maybe James Bond, W7. And for the last one, is the most challenging one. We spent over a year to eventually work it out through a very, I would say, special mechanism. May not be the most smart way, but it works. So as I showed you just now regarding wrinkles, so wrinkle formation takes time, and the wrinkle release takes time too. So from wrinkle to flat, the process is called relaxation. And as you can imagine, the relaxation can only happen when the top surface remains to be wet. When it's dried, you cannot change it. This is like we make cookies in kitchen. You can reshape cookies whenever you want before you bake it, but once you bake it, you cannot reshape it. So this is the same thing. And therefore, in order to make the permanent wrinkle, what we try to do is that we want it to relax very slowly. Basically, it takes a longer time to relax than the time to dry. And therefore, before it relaxes back to be flat, it is already dried, and then we can, of course, fix the wrinkle. So with that, we did a so-called gradient wrinkle formation, and now you will find that initially, you form wrinkle, and now it began to relax, but before it relaxes completely back to flat, it is already dried. And once it's dried, we basically fix the morphology, and it cannot further relax to be completely flat. Or someone may say that, hey, you can possibly re-wet it. Well, you can re-wet it, but during the re-wetting process, we actually have it swelling even more. And therefore, it will actually generate more wrinkles instead of less wrinkles. And because of that, the wrinkle will always stop at this stage. So we actually also made a small device for demonstration. So here we make a label called a water-sensitive label and put it on a computer RAM, wet it, and then dry it. After dried, you can observe a pattern of H2O, which basically gave people a gentle reminder or warning that this part was wet at least once, because our small device, the label, can record the history of wetting. Even it was wet only once, it can record the history, and therefore to show the trace of the history. And now we are using this label for some other applications like food packaging. We can, of course, use many other means to make wrinkles. We can use mechanical means. We can also use laser to generate wrinkles, like what I showed you just now. And basically, the phenomenon is all the same. And the mechanism is also the same. We would like to deform the surface and eventually retain the deformation, and to generate different surface morphology and generate contrast of the transparency to show patterns. So now I will move to the very last one. So what I showed you just now is that we have a coating on a very soft substrate. And after absorb moisture, it will swell. It will swell both XY direction, but less on the Z direction because this is a very flat surface. Now, if we put this coating on a very rigid substrate, as you can imagine, if the substrate is very rigid, you can barely swell on the XY direction, but more on the Z direction. And with that, we can change the thickness. And if we can change the thickness, we can also make something pretty interesting and unique. So a little bit of background about iridescence and structural color. I think it's very well known in the field. Example like peacock feather, butterfly wings, they have very unique 3D structure and therefore to show beautiful structural color. But the simplest structural color is soap bubble. Basically, because of the very low thickness, it's in the same range of the visible light, and therefore it will show beautiful color. The reason the soap bubble show different color of bluish, greenish color is because of the gravity generates a little bit of deviation of the thickness. And another example of structural color from this kind of thickness change is nacre. Pearl is the most popular, I would say, decoration items in our daily life because the multi-layered structure of nacre, it can generate light interference, and therefore it can generate this beautiful iridescence and a nice smooth color. So we figured that since our coating is very thin in submicron range, and therefore if we make our coating into the thickness of the visible light range, then we can generate a similar color. Well, yes, this is what we made. So this is a small device with a very low thickness. And as you can tell, if our thickness is similar to the thickness of a soap bubble, then we can have a very similar color. Actually, a little bit of deviation of a deviation of the thickness and generate a little bit different color, but will match the color of the soap bubble. But of course, as I already showed you just now, that we can do this coating using different methods and control the parameters, generate different thickness. And if we generate a different thickness, like I showed you here, if we intentionally generate coating with different thickness, then again, we can generate different structural colors like shown here. And not just generate the coating with different thickness, as I mentioned at the very beginning, through the swelling process, we can actually change the thickness. So when we spray moisture on the surface now, if the coating is coated on a very rigid substrate like silicon wafer, then it can change the thickness from very thin to reasonably thick. And during the process, because of the change of the thickness, again, it can change the color. So here, statistically, you can see the color difference, but also dynamically, you can also see the change of the thickness and lead to the change of color. And this is, of course, a reversible process, and we can make this change for many, many cycles as you want. Well, now I already showed you that we can show different colors, we can show color change, but if we apply the same trick I showed you just now, do a cross-linking regionally, then you can imagine after we do regional cross-linking, the cross-linked zone can barely change thickness. This is a similar mechanism we talked about in the wrinkle section. So the non-cross-linked zone will be very sensitive to moisture and therefore to change thickness. And therefore here, you will find that if we do regional cross-linking, the cross-linked zone will barely change thickness, but a non-cross-linked zone change thickness, we can generate patterns. So it's a very simple design consideration, but it works very well. Well, this one is very decent. We can embed a pattern. We can show a pattern whenever needed. And on the other end, if we would like to make it even more versatile, what we try to do is that maybe, I think for certain applications, eventually, for security reasons, for example, you would like to completely erase the pattern after the part finishes the mission. We would like to damage it completely erase it. So we can do the same thing. As I showed you just now, here, this is through a so-called permanent cross-linking. And if we do permanent cross-linking, then of course we cannot change. But we can also do a so-called reversible cross-linking. And if we do reversible cross-linking, for example, using boric acid to do reversible cross-linking, the cross-linked zone can be reversed, be recovered, and the decross-linked come back to regular thermoplastic. And very fortunately, we can just use high temperature to do the decross-linking for boric acid cross-linked zone. So here, we do a very simple device. So this is the one cross-linked one with boric acid. So from the beginning, every time we spray moisture, you can observe the pattern, Yukon pattern. But then we can also use steam to heat it. After we use steam to heat it, we dry it. And after we dry it, you will find that it no longer shows the pattern anymore. And this is because it's completely decross-linked. So I'm sorry that there is a little bit of noise. I should avoid it. Basically, you can find that with proper reversible cross-linking, we can control the formation of the patterns. We can keep it as long as we want, but whenever we don't need it, we want to erase it completely. We can simply use the high temperature steam to treat it, to decross-link, and then the pattern can be completely erased. So with that, I would like to thank all my co-workers and collaborators, and also the sponsorship by Connecticut, particularly for the last part. Thank you very much.
Thank you, Professor Sun. Thank you for the nice talk. And it's really very magic. We can see the smart materials made from soft material. Now we can start the open mic session. Maybe we can start from Professor Siu. I have collected some questions, technical questions about your talk.
Okay.
Yes. So firstly, I want to know the minimum thickness of the crystal silicon for the solar cell, including the substrate and the nanowires.
Yeah, actually, that's a good question. We can decrease the thickness as thin as possible, but problem is we can consider two things. First thing is that the practical fabrication issue. So if the substrate is too thin, it's not easy to control during the fabrication process. So in our laboratory, we tried about up to 10 micron thickness, but so far the reproducible fabrication process required about 20 micron as a minimum thickness. But other researchers, such as Ichi group in Stanford, already reported that is around the 1 to 3 micron thickness substrate. But I think that is not quite feasible for the practical fabrication. And second issue is that the light absorption capability of the silicon substrate. So the although short wavelength region of the light is very easily absorbed by the silicon substrate, despite of the indirect band gap of the materials, but at least based on the theoretical simulation, about the 50 micron thickness is the optimal thickness to absorb the instant light completely. So by considering two issues, we can choose optimal thickness for the flexible application. That's the reason why I did the experiment between 20 micron to and 50 micron range.
I see. Yeah. You have shown us the flexibility of the solar cell.
Yeah.
I'm wondering, is it sitting on some substrate, or it's only the silicon substrate and the silicon nano structures?
Actually, based on our work, we use the micro wire at the micro scale diameter 2 micron. So instead of the nano wire, so micro wires form on the substrate. So during the bending test, we only with the silicon. So micro wire on the silicon substrate. But for the practical use, we can apply the polymer layer on top and bottom as a capping material. So it will make more stable in the real application. But during the test, we didn't use the polymer layer on top and bottom.
I see. So, how about the area of the flexible solar cell and the cost?
Oh, okay, that's good question. Actually, size. You mean the size of the device, right? So
Yes.
this work, I showed only the 1 centimeter by 1 centimeter unit device, but in fabrication process, we can easily extend the size up to the practical scale. For example, M2 or M6 scale is that is the 16 centimeter by about 16 centimeter is the standard size of the conventional industry commercial structure. That's not big problem. So only the facility issue. So in general in university we have a semiconductor based the semiconductor oriented device facility. So that's the reason why we fabricate a 4-inch wafer scale process. So to increase the total number of the device, we set the size as 1 centimeter by 1 centimeter, but so far we demonstrate up to 4-inch wafer scale device, and we believe that it is very easily extend to the real practical size in used in industry. Regarding the cost, it's not easy to say, because all other process step is exactly identical with the conventional fabrication process of the industry. The only different part is the micro wire fabrication step. So in general, I use the dry etching facility, dry etcher for the micro wire fabrication. It is a little costly, but meantime, we also can apply the solution-based etching method to fabricate the microwire structure. So if we apply the wet chemistry-based fabrication process into the device fabrication, I think that the cost is not the big issue. Meantime, flexible device is the high-end application, so maybe the cost is not the big problem.
Yes, yes. So actually, my own field is related to flexible electronics, and we are particularly interested in electronic fibers and tactiles. So sometimes we focus on how to solve the air breathability. So I'm wondering, for the solar cell, is it possible to make them make them breathable? I mean, the air can go through the solar cell.
I mean, transparency.
Yes.
Okay. So,
yeah. Just like the fabric. Just like our clothes. Is it possible?
You mean that light can pass through the solar cell, right?
The air can pass through the
Oh,
solar cell.
you mean air? Yeah. Actually, yeah, that's very good question. Actually, one of my research topic, except the flexible device, is a transparent device. So
Yes.
to make the transparent solar cell, we apply the microscale hole into the silicon substrate.
Oh,
By
I
applying
see.
the microscale silicon microscale hole into the silicon substrate, and by arranging that hole with certain geometry, we can make this silicon vapor invisible to our bare eye. So,
Yeah.
but in that case, while we make the silicon vapor transparent, meantime, because there are many holes in the silicon vapor, although it is not visible to our bare eye, so air can pass through the silicon substrate.
Okay. Okay. Yeah, that's interesting.
Yeah.
Yes. Thank you. Yeah, thank you. So Professor Sun and Professor Tik, okay. Do you have any questions for Professor Siu?
Yes,
Oh,
I have
yes.
a real quick question, Dr. Stu. It's a truly impressive talk. I was very impressed by your I would say nano micro fabrication techniques to make such elegant tools. I wonder, just out of curiosity, does your device perform better at a flat position or a little bit banded position? Would you achieve even high efficiency when it's slightly banded? I'm just curious. Efficiency will be even high at slightly banded?
Yeah, that's really, really good question. Oh, actually, although you are working on a different topic, but you asked really, really key question to in the solar cell application. Yeah, that's the really important question in the solar cell field. In the concave and convex, the bending, the efficiency change or not, right? The problem is that when we estimate the efficiency, we always consider total the surface area. So the as a point of the right trapping efficiency, maybe this kind of bending is beneficial with a bit, but you know what, the surface area is less. If we measure the total area, so it is not easy to say which one is better or not. So yes, there's
I see. I got your point. Yeah, that makes a lot of sense. It's we should consider the entire bigger picture instead of the regional. Thank you.
Thank you for a good question.
Yeah. So yeah, I saw Professor Tik, okay, is there.
Yeah,
Yes.
excellent.
Yes, I finally see you.
Yeah, I enjoyed your talk very much. Thank you very much.
Yeah.
Yeah. So, your device has a very large surface area. So, have you looked into the effect of functionality due to the contamination of the surface by airborne substances?
Oh yeah. That's good question. Actually, because we use the one-dimensional structures, the surface area is much larger than the planar surface.
Yes.
So, in case of solar cell application, we are concerned the surface recombination rather than the surface contamination. So to passivate the surface and protect the surface, we apply the oxide material on the surface with the atomic layer deposition method. So very thin layer of the aluminum oxide is applied on the surface. That layer can passivate surface to minimize surface recombination, and also they can avoid the surface the contamination by other chemicals, I think.
Okay, so you mean that if the surface area is covered by the oxidized materials, so it cannot be changed efficiency.
Oh, yeah.
Okay, so this means that can the gaps in this device be filled with soft materials to prevent the surface contamination?
Yeah, sure. Yeah, that's the good question. Actually, the end of my presentation, I mean, the last one quarter, the part, I briefly explained the PDMS-based surface protection. So the soft material is very important material, I think, that for future solar cell application. So soft material can protect the surface from the dust or water or any other contamination. And also, meantime, they can be used as a radiative cooling materials to manage the surface the device temperature. And meantime, also the soft material, if the soft material has the surface structures, and also can reduce the surface reflection and enhance the better light angle instance. So I think the soft material is very important topic in the solar cell application, I think.
Okay, yeah, thank you very much.
Thank you.
Yes, it's a very interesting point. Actually, I also noticed the PDMS layer on your solar cell. So I'm thinking about if we use Professor Tikasuo's and Professor Tikaoka's film to replace the PDMS on your solar cell. I don't know, all Professor Swin's colorful film, the color changeable film. I don't know if we can have some very maybe interesting devices.
Yeah, I agree. Yeah. So good.
I think Dr. made a really great comment. Actually, we have been thinking about, because the wrinkled surface, they can kind of scatter diffuse light, basically can let lights go back for multiple cycles, and it may kind of like help collect to minimize the refraction, basically to minimize the refraction and to let the light stay. I don't know whether it will help. I'm not in this field, but just had a similar kind of thought as Dr. Zhang commented just now. So it's thanks.
Yeah, but actually the wrinkle surface is very popular in the polymer-based solar cell the field. So over more than 10 years, people are using the wrinkled surface for better efficiency of the organic solar cell. So it is the
okay. Well, it's not new. It's already explored. So it's great to know.
Yes. Okay. So now I have several questions for Professor Tikaoka.
Yeah, go ahead.
Yes. So you have used the silica particle of 110 nanometers. So have you tried other diameters?
Yes.
So,
yeah. Basically, we used the size of sub-micron size of silicon particles. So if you use larger particles, that exhibits the structural colors. But in this case, this material exhibits the transparent colors when you use less than 150 nanometer particles. So in this case, we use the smaller particles to obtain transparent without colorless materials.
I see. So you have tried to tune the concentration of the nanoparticles in the film. I see it's up to 40 percentage.
Yes,
so
40%.
Yes. So how about the result if we further increase the concentration of the nanoparticle in the film?
Yeah, it's difficult.
Oh.
Yeah, the particles aggregate each other in the suspension. So the maximum volume fraction of the particle is about 40.
Okay,
Yes.
I see.
Yeah, but you can change that. Yeah, if you do it. Yeah.
Okay, it's very interesting because both the modulars and the brick and the length at brick increased.
Yeah.
So what is the reason for the simultaneous improvement in tensile strength and the elongation of the composite?
I think there exists a hard thin region of the polymer matrix around the silica particles. So it makes the composite materials becomes more tough. Yeah, but for the MEL2 MA case, but if we use MEA, PMEA as the polymer, the SS curve is totally different. It exhibits the J-shaped curves. You see, so in that case, we can't see any hard region of the polymer matrix around the silica particles. So this is the reason why there exists a difference between the mechanical properties of these different elastomers, composite elastomers.
I see.
Yeah.
Yeah. It's interesting. Yeah.
Thank you.
Yeah.
Also, our materials is just a mimic of a cornea, which is a transparent point of an eyeball, you see. So eyeball can be prepared by mucosaccharides gel and then the collagen fibers, composite materials. So in the mucosaccharides gel, the collagen fibers arranged in the parallel in case of a cornea. So the cornea is transparent. But the sclera, which is a whitish portion, is a target. In that case, collagen fiber is arranged randomly. So this is a difference between them.
I see. Thank you. So do Professor Sun or Professor Liu have some questions for Professor Tikaoka?
I have a quick question, Dr. Akioka. Truly impressive all kind of work. I cannot imagine that it may recover to be transparent as you initially commented use the rubber example. But I have a further question, just again out of my curiosity. So if your particle has a color, and it's for example carbon black, instead of using silica, if you use carbon black, I mean of course carbon black may not be colloid or very uniform shape, but for example some other polymers like polystyrene, they are, I mean if they are not perfectly transparent, they even have a color. And would you show the same phenomenon that at a certain range it will recover to be transparent?
Thank you very much. In case of the polystyrene, which is whitish particles,
yes.
It's not transparent. Yeah. So in that case, we can obtain the same type of transparent elastomers. But in the case of carbon black, when we use the colored materials, the resultant elastomer becomes also black.
Okay, because black really absorb virtually everything. It's too difficult to handle.
Yes, that's it.
Okay, I see. But it's really impressive that even for polystyrene spherical particles, because polystyrene could be pretty opaque at a small size, but you can still recover back to transparent, which may bring some interesting applications. So it's I will go back to reading your paper carefully and then learn more. Truly impressive work. Thank you.
As you can see, you are studying about the structured materials. You can easily obtain such transparent colorless materials.
Yeah, I think we can definitely learn a lot and kind of take advantage of you already built. So thank you.
Yeah, it's a very simple point. In case of structural colored materials, the peak when you apply a light, you can obtain a peak in the reflection spectra in the visible region. But in our case, the peak can be observed in the UV region.
Okay, that's the point. Okay, that
very simple.
Okay, that's the I like it. I will definitely discuss with my coworkers. I got some new ideas. Thank you. That's really interesting.
Even the structural kind of materials, the materials can be transparent.
Yes.
Because of the presence of the odor of the materials. Yeah.
Yes.
Okay.
Yeah. Also,
Hi, Joey.
Hi.
Okay. Good night. Good evening.
Good evening. Thank you very much for your invitation.
I'm Zibun Wang from Jiangxi Normal University. I graduated from the Nagoya Institute of Technology. Yes, sir. So I have a question about Professor Sun.
Oh, yes.
Okay, just now I listened to your presentation about the colorful bubbles. Use a simulator to make the colorful bubble and use the PVA.
Yes, we use polyvinyl alcohol. Yes.
Yes, and then I found in your process you also coating the gold and the platinum like a PT on the subject.
Yes, we do it because we can achieve similar performance, but not that ideal performance. The reason we coat a very thin layer of metal is to generate very different refractive index, so that we can generate a more vivid effect. It's kind of
how about the thickness of the AU and PT?
Oh, very, very thin. We of course try to make it very thin so that it will not affect the other performance.
Can we change another metal like nickel or another?
Yeah, I believe the purpose is to alter the refractive index, and therefore you can use other metal. Of course, we use gold and platinum or palladium because it's highly available. We basically use regular sputter culture from SEM lab, but you can use other metals that works as well.
Okay, so thank you. And you also mentioned you will adjust the thickness, maybe lace. So and you can change the color.
Yes.
How about is important for the PVA's concentration?
Yeah, you can use low concentration and coat multiple cycles, but you can also use relatively high concentration to coat less cycles. But we do observe that actually coat multiple cycles generate a kind of more uniform system and appear to be more ideal. But I think it all depends on the fabrication technique. Like what Dr. Su's technique is really amazing. It's like control so well. If we can control so well, I think we can definitely generate other results without worry about concentration or cycles. But for our coating technique, we have to use relatively low concentration of suspension to generate very uniform coatings, and therefore we choose to coat multiple cycles.
Okay. Thank you, Professor.
Thank you for great questions.
Yes, so maybe I have another small question for Professor Tikaoka. So you have tried to make the transparent tunable film. So how about is it possible to make them into fibers?
Yeah,
maybe
it's possible.
Transparent tunable fibers?
Yes, my student, who is a Chinese student, is now preparing that in our laboratory.
I see.
Yeah, it becomes tougher, and then also colorless, transparent. Yeah, you can have structured color fiber.
I see.
Yeah.
I see. So it is elastic and transparent tunable fibers, right?
That's it. We can control the elasticity, also transparency on the color.
Very interesting. Yeah.
Thank you very much.
Yeah. So time is very short. So finally, we have many questions. Still have many questions. So Professor Sun, I got maybe I select several questions for you.
Sure.
Yes. So how about the stability of the coating film on the on the substrate. You
That's
can, yes,
yes,
you have,
that's a very good question. I actually worked in industry before returning back to academia. So, stability, reliability, and also reproducibility and also cost, we care it very much. So,
yes.
yes, we can keep the surface coating very stable. So what we did is actually a very simple technique. We cast a very thin layer of PDMS on the surface again. So basically, we sandwich the coating in between two layers of PDMS. The bottom layer is the one to serve the function. The top layer of PDMS, very, very thin, maybe micron range, is to do the protection. So with that, we can make the device very stable. I don't have time, but we did 50,000 cycles of we did 50,000 cycles of cyclobilic test, and the sample can still remain to be highly reproducible even after 50,000 cycles of stretch and release.
Okay, I see. Great. So second question, how about the response time of the film to change its color, and the recovery time?
It is instantaneous because
really?
it's not like yeah, because our technology is based on the physical blocking. So when we release, the cracks close. So once it's closed, it's blocked. So basically, it's without any delay, I would say, virtually no delay, because this is all about physical blocking. So when you open it, you can observe it. When you close it, immediately you cannot observe it. So it's a very instantaneous process without delay.
Yeah, this point I can understand. So how about the humidity responsive change?
Yeah, that's a good question. This is a really great question. We choose PVA because it's a very good material and because it's sensitive to moisture. But on the other end, I understand the concerns in terms of stability. What we did is number one, I showed that just now that I mentioned just now that we can coat a very thin layer of PDMS as a very protection layer. And on the other end, we can also very gently, very briefly cross-link PVA, very, very lightly, not, heavily cross-link, but very lightly cross-link PVA so that it can remain to be sensitive to moisture, but on the other end, it will be very stable. So we use these two kind of means to control and to achieve high stability.
I see. Very, very interesting. Yeah, thank you. So, is there any other questions for Professor Sun from?
I have a question. Actually, your talk was very interesting to me. That is the slide itself is very fascinating, and then the explanation also is very interesting. Thank you for that.
Thank you.
I impressed that is your research topic is really related to the our nature and then our daily life. So you found the research idea from the nature with the daily life. So it is a very simple question to find the very nice idea regarding your research. How do you train yourself? So could you explain that?
This is a difficult question, but Dr. Xun, I would say like I would appreciate all the variable I would say input from my students. Actually, quite some ideas are from my students and my coworkers. And on the other end, I would say I'm very lucky that we have a bigger group of undergraduate students. I cannot afford a big group of PhD students, but fortunately, I can have a pretty large group of undergraduate students, and those young guys have very wild ideas. Another good thing is that I mentioned just now, I worked in industry before returning to academia, and I do talk to many industry partners and collaborators, and they actually give us very, very tough questions. But on the other hand, their question really drive us to think more, be better prepared, and that tend to be very helpful as well. So I think we just try to keep our mind open, and that really help us to think a little bit broad and deeper. Thank you.
Yeah, thank you for nice comments.
Thank you.
Yeah, thank you. Let's keep our mind open. I think it's very impressive talk from both of you. So we are already five minutes delayed from the agenda. 2,000, we have 2,000 audience, more than 2,000 audience from the other. So a kind of magic material. Yeah, thank you for your sharing, thank you for your time.
Thanks for this great opportunity.
So much.
Thank you.
Yeah, thank you very much. And I hope maybe sometime in the future we can meet with the audience. Maybe we can have real talk. We can see each other. Yeah. So
truly
now
look forward to it.
maybe yes. So this session is closed. Thank you very much.
Thank you so much.
Thanks a lot.
Yeah,
thanks a lot for this opportunity. Bye-bye.
Yeah, see you in the future.
Have a great night. Bye-bye.
Bye.
Bye-bye.
Yeah. Bye.